Okay, so what we're going to do here is reinforce material that's been covered in the lecture, and then give you practice to build functions that will help you check if a set of vectors is linearly independent. And then we could do the same functions if we wanted to check if one vector is a linear combination of the others, because if we have set A and we have a vector and we want to know, is it a linear combination of this? Well, we figure out how many linearly independent vectors there are here. If we add this one and it grows, then it's not linearly independent of those. I mean, it is linearly independent. If it grows, it's linearly independent. If it doesn't grow, then it is dependent on that. So being able to check for linear independence allows you to do linear combinations in an effective way. And what seems kind of weird, we've been using our really good friend, the LU factorization, lower upper factorization, which is at the heart of solving systems of linear equations, AX equals B. But unfortunately, it's not good enough for counting the number of linearly independent vectors in a set. So we're going to go through examples that show you where LU fails and how a refined version of LU factorization, where the U is written as DL transpose, that does allow you to count precisely the number of linearly independent vectors, and also how using the permutation matrix allows you to take vectors that are independent, dependent, and all mixed up, and by reordering the columns of the matrix, move the independent ones to the front. So you can just grab them, okay? Instead of getting the first one, the 13th one, and the 27th, you can just move those up to the front and grab the first three, if that's the number of linearly independent vectors. So that's the idea. Okay, so the uber pro tip is that if you have a matrix that's of the form A transpose times A. So if you go to the appendix of the book, there's a special type of matrix called positive definite, positive semi-definite. Mani mentioned these in lecture. They are matrices that always have this special form, A transpose A. And that's where the LDLT factorization always works. It says you take A transpose A that we used in the pro tip for determining linear independence or not, and we modify it just a little bit. Instead of only having one permutation matrix on the left, we add its transpose on the right to preserve symmetry, and instead of writing U, we take a very special way to write U as the transpose of a lower triangular matrix, so that will make it upper triangular, and then we multiply it by a diagonal matrix which preserves the upper triangular property, and that diagonal matrix will have non-negative entries. Non-negative means 0 or positive. And the number of non-negative entries on D, the number of positive entries on D, because all of them are non-negative, the number of positive entries on D is the number of linearly independent columns of the matrix A. And so that's really, really nice. And then we'll talk once again about how A times P transpose moves all of the independent columns to the front. So we're going to just do a quick examples, and then we're going to have you do some programming based upon this. So LDLT factorization versus LU. And so we just want to illustrate, do we really need to use the enhanced version? And the answer is yes. And if you just want to accept that, that's fine. So we'll just run this cell. It's simply creating a upper triangular matrix, and we see that it has all zeros on the diagonal, ones on the super diagonal. And so it's upper triangular, so we expect an LU factorization of this matrix would be the identity matrix, which is lower triangular and upper triangular. The identity times A is already an LU factorization, so this should be U, and we can just run it and check it. Yep. So I just used the LU factorization command native to Julia, and we see that its diagonal is all zeros, and then I pulled off U by the dot command, f.u picks out the entry in that structure, and sure enough, it's the same matrix we had. And we see that if we just did LU on A itself, all of the entries on the diagonal are 0, but yet our matrix has, okay, that column is 0, but this is E1, the first canonical basis vector. This is E2, the second canonical. This is E3, and those 3 vectors are linearly independent. So A has 3 linearly independent vectors, and if we were to just apply LU to A, the diagonal of U tells us nothing, okay? You cannot read it off of that. Now, we know that we're supposed to be looking at A transpose A, so let's just do that. So we'll apply the LU factorization to A transpose A, which is what we're supposed to be doing. So we just do it. We just do it. Okay, so now the diagonal of U has 3 non-zero entries. And our A matrix had 3 linearly independent columns. So in this particular example, when we form A transpose A and we do the LU factorization, it's telling us the right answer, okay? So in this particular case, you do LU factorization on A transpose A, and if you just look at the number of non-zero entries on the diagonal of U, wow, that's the same as the number of linearly independent columns of our matrix A. But that is not true in general. So what I want to do is prove to you that you have to use LDLT. So we're just going to hunt for a counterexample. So this is kind of fun. We're just going to do an organized random search. So this function is going, okay, this is just the LDLT that's in the book that I wrote. Not super efficient, but easier to understand. And now I'm just going to do a random search. So I'm building a function called counterexample because I'm hoping to find one. I just fix the seed so that all of us, when we run it, we always get the same answer. And instead of doing a for loop, because I don't know how many times I want to go through, I'm going to use another looping method called a while loop. And it starts with a while and an end, so it's just like a for loop. And then we're going to go until as long as this condition is true. And so I just called it flag. You can call it anything you want, and the flag is 1, so this is true. And then if we ever find our counterexample, I set the flag to 0. This will be false, and then we will exit the looping process. Okay, so I'm just going to build matrices that have linearly dependent columns. So I just take a random matrix B, I take another random matrix, and I take some of the columns of B, I take some linear combinations of those, I take some of those other columns and I just mix them all up by putting some in the middle, and I'm going to apply LU factorization to A transpose A. I'll get the diagonal of that, and I'll count the number of entries of the diagonal that are non-zero. And to do that, I just say, find all of the indexes of absolute value diagonal of u such that the, well, I should have done it such that x is greater than 1e to the minus 10, then I wouldn't have to do this n minus. So I'm improving my programming as I explain it to you. Okay, so here I'm counting the number of 0 entries and then the size of my diagonal minus the number of zeros, the number of non-zero. So smarter would have been x greater than 1e to the minus 10. And then I could do it. The number of linearly independent predicted by LU would simply be the length of this index set of indices. And now apply LDLT to A transpose A and do the same trick where I will count the number of 0 entries and then subtract that from the size of my matrix, which is, okay, not the smartest thing. You guys will fix it. And then I'm just going to loop through until LDLT tells me an answer that's different than LU, and then I'll check to see if that answer is right. Okay, so I'm just doing a systematic search, brute force, and then I'm just generating random matrices. So how many times through is it going to take before I get a counterexample? 7, 400,000, 20. Okay. So I've created my function. I also did another one where all of these entries that are 1 times 10 to the minus 10 or smaller, I'm just going to set them equal to 0. I'm going to call that a cleanup function. It works on matrices or vectors. Okay, I'm going to run my counterexample. Second time through. How did I get so lucky, Monty? Can you prove that I should get lucky that we can go? Yeah, so it's apparently not that uncommon that LU lies to you. Okay, so the diagonal of U with LU says that I have 2 linearly independent columns. And then when I do LDLT, I get the real answer, which is 3. Okay, so you cannot get the number of linearly independent columns by simply applying LU to A transpose A. You really do need to apply LDLT and look at the diagonal of D. So we'll go just a little bit farther. So this is the U matrix that comes out of LDLT. So this is the D times L transpose. Okay. We see it has 3 non-zero entries on the diagonal, and then it's 0 all the way after that. Okay. Here I'm going to take my A matrix, and then using I'm going to permute using the permutation matrix from LDLT. Okay, so you can't really tell if those rows are linearly independent or not. So I'm just going to check it. I'm going to do it for the original A matrix, look at the first 3 rows, and then I'm going to look at the permuted matrix, its first 3 rows, and just look at the diagonal of D. Okay, so these are the same D elements we had before, so that's cool. Whoops. And here we see that the first 3 columns of A, so I've got a new matrix, I did LDLT on that, I look at its diagonal, yeah, it's only the first 2 columns of A were linearly independent, the third one was linearly dependent on the first 2 columns. But if I transpose, take A times P transpose, then I'm able to move those columns to the front, and I get the 3 linearly independent vectors. Okay, so that's the bottom line. We need LDLT. And if you want to get the independent vectors up front, just form A times P transpose, and it moves the independent columns to the front of the matrix. And how many of them are there? The number of non-zero entries on the diagonal of D. So that's how you check the number of linearly independent vectors. Okay? That's how you can verify all this with Julia. So what John is going to take you through now is some programming exercises. And you want to plug in your laptop, John?
We can keep it on here.
Yeah? Okay. So here's the first exercise, is using the LDLT function that we've provided. Write a function that counts the number of independent columns of A. I thought you said all that would be taken out, John. It's just not in mine? Okay, so that's what they have? Okay, so I'll hide mine, and I'll let you plug in over here, okay? You gonna plug in?
Yeah, I think so.
You take straight HDMI?
Yeah.
Perfect. Okay, fortunately, mine wasn't on there long enough for you guys to memorize that answer. And then why don't you use this? It'll be easier for you.
Thank you. Okay. Good.
Turned on? Yep.
So on the version of the lab that you pulled, is it showing the answers for these 3 problems? Okay, good. So
I'm the prof. I get all the answers.
So problem 1 here, using the above LDLT Rob 101 function that we provided you, and the above method of determining the number of linearly independent vectors in a matrix, complete the function num independent vectors, which takes in a matrix A, here, and returns the number of linearly independent vectors. So these next 3 problems will basically build up to a very helpful function, which will allow you to determine whether any matrix you feed in and any solution matrix and any matrix B, whether that has a set of unique answers. So put your code in there, and we'll come back to that in a minute.
Yeah, so when you're done, you'll be able to take AX equals B, rectangular. It could be 100 rows and 2,000 columns, or 2,000 rows and 100 columns, and you'll be able to check in a microsecond whether it has a solution, and if it does have a solution, if it's unique. Think about it, the power, the power.
Anyone? Okay, cool. So I'll start going over it. So we start this off by calling LDLT Rob101 on matrix A. That'll give us our very helpful matrices, which we will use to determine the number of independent vectors. Then we'll do a helpful for loop here. When you're doing your for loop, make sure you're doing size d comma 1, because although diag d is going to be a vector, which means it won't have a second dimension, it'll only have one dimension, what'll happen is Julia's size function will still return a tuple. Even though the second value of the tuple will literally be nothing, it'll still return a tuple. So you still have to do comma 1 there. Inside the for loop, we're going to check if we have a non-zero value. If we do, that means we have an independent column there. So we'll add 1 to sum. Once we're done looping through everything, we'll just return sum. Oops. Pardon me while I have to rerun everything. Oops. Then we'll run it. We'll see that A has 3 independent columns here, and that B has 2 independent columns. This is what we expect because 2, 4, 6 is obviously a multiple of 1, 2, 3. So we know that we wrote the function right. Now we'll move on to problem 2. So for problem 2, we're going to use a pretty helpful facet of linear combinations. We know that the vector v0 is a linear combination if and only if the set v0 to vm has the same number of linearly independent vectors as v1 to vm, with the idea being that the extra vector v0 is not independent. So we'll check that pretty easily. You can kind of see how to do it here. You're going to write this function is linear combo, which takes in a vector v and a matrix A matrix in this case just being a collection of column vectors, and returns true if v is a linear combination of A and false otherwise. So false if v is not a linear combination of A. So this one should be a little quicker because you can use the function that you just wrote to solve this expediently. Yeah, so I'll just put in the answer here real quick. We're going to lean on our previous function that we just wrote. So you'll have temp is equal to A, V. What that'll do is it'll basically just concatenate matrix A with vector V. So we'll get a set from V0 to Vm in terms of this green box here.
If I get a new...
We'll check how many independent vectors there are before we do the concatenation, and how many independent vectors there are after we do the concatenation. And if there's the same number of linearly independent vectors before and after, we deduce that whatever we just added is dependent, so we return true. Otherwise, we return false. I clearly spelled something wrong.
And then if you put it here.
And there you are.
It's easier to see what.
So for problem 3, this is basically the fastest part, but in the spirit of giving you a little bit of time here before Tribby begins her recitation, I'll just work this out up here. So what you're going to do is you're going to check the number of independent vectors that exist in A. There you're going to basically check to make sure that all of the vectors of A are linearly independent. That'll ensure uniqueness. And then we're going to check that B is a linear combination, of course. B is a linear combination of A. That'll check that the solution exists. If the solution exists and it's unique, we'll return true. Otherwise, we'll return false.
And just to be clear, John could have said else return false. That would have been very elegant too.
Yep.
That's just the way I would have coded, okay? This is perfectly correct. Differences in style, okay? But I think if, then, else, that's my mathematical brain kicking in.
Well, I like programming it like this sometimes because if you want to go back and add in more checks later, like if you want to add in an else if comparison maybe, then you just know that if the conditions aren't met, you'll return false. If special conditions are met, you're returning true. So it's really just a matter of style. But anyways, that's how you do that. And you see down here it works because our vector is 12, 15, 19. And our matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9. And you'll notice that 12, 15, 19 is just the row sums of A. So of course it has a solution. The solution is just 1, 1, 1. And as expected, our function says, yes, a solution exists, and yes, it is unique. So we are done. That's a function that you can make to tell you if any vector and any solution vector have a set of solutions that are unique, which is very helpful.
All right, can y'all hear me? Perfect. So we're gonna go ahead and get started with our recitation. So my name is Eva. I am a 5th year PhD student with Professor Grizzle back there, and I'll be helping out Tribby with the recitations. So today we're just going to be covering matrix determinants, inverses, linear independence, and yeah. So let's go ahead and get started. Cool. So the first thing we're going to do is we're just going to recall some of the facts that we know about determinants. So the first thing that we know is that given that A is a matrix, we know that the determinant of A is a real number, right? We also know that a system of equations, AX plus B, right here, that system of equations has a unique solution if the determinant of A is not equal to 0. However, when the determinant of A is 0, A may have an infinite number of solutions or no solutions at all. The other thing here is that if your matrix A is a 2 by 2 matrix, you can use this formula over here to find the determinant. Any questions so far? This is all just a review, yeah? Cool. So now let's talk about some additional facts of determinants that we learned this week during class. So the first one is the determinant of a product of matrices. So let's say that we have A and B. Both of them are n by n matrices. What is the determinant of A times B? Well, the determinant, ooh, Trivy, something happened. So I use an iPad, not a Surface. Great, what did I do?
I think you just hit the taskbar.
Perfect, awesome.
Actually, let me just put this in tablet mode.
There we go.
This should be better.
That is a lot better, thank you. So do we have any guesses as to what the determinant of A and B would be? Anybody? Yes. Correct. Nice. So determinant, wow, of A times determinant of B. This thing is angled. The tip of the pencil is angled to one side, so interesting. So given that we know that, here's another question. If we have the LU factorization of A, what is the determinant of A with the LU factorization? Anybody, come on. Do we have Professor Ghaffari in the back? Yes, go ahead. Perfect, there you go. So let's go ahead and, Truby, your pen is just L times determinant of U. I apologize for the handwriting in advance. All right, any questions about that?
I don't have a question about that, but is there a spot where we can get the PDF?
Ooh, I guess we forgot to upload it. Okay, cool. Truby will take care of that right now. Awesome. So the next fact that we learned, I think, this week is that if A is a triangular matrix, then its determinant is going to be the product of the elements, of its elements on the diagonal. So what do we mean when we say triangular matrix? Any guesses? Yes. Yes.
But either one is when, for your lower triangular matrix,
Yeah.
all of the elements below the diagonal or above the diagonal are zero,
Or vice versa.
or vice versa.
Yeah, so thank you so much. So with triangular matrices, you have two types, right? You have the lower and the upper triangular matrix. And the lower triangular matrix is when all the elements of the diagonal, below the diagonal, are zero, and the reverse for the upper. So all we're saying here is that, for instance, if I have an upper diagonal matrix that looks like this, what this tells us is that the determinant of this is equal to 3 times 5 times 9. That's pretty cool, right? Any questions on this? Perfect. All right, and here's just an additional fact, which is if you have P, which is a permutation matrix, then its determinant is either going to be plus or minus 1. Any questions so far on determinants? Okay. So let's move on to the inverse of matrices, right? So let's say that let's first define what it means for a matrix to be invertible and what its inverse is. So we see here that a matrix A is invertible if there exists another matrix, which we call A with the A minus 1, such that when you multiply these two matrices, you end up with an identity matrix. Do we all know what an identity matrix is? Yes? Can you tell me what an identity matrix is? Perfect, yes, that is exactly what an identity matrix is. So let's take a look at some facts about matrices and their inverses. So we know that a matrix A is invertible if its determinant is not equal to 0. And you might ask, why is this the case? Well, let's take a look at this 2 by 2 matrix over here. We can see that when we find this determinant, we are dividing by when we find the inverse of this matrix, we divide by the determinant, right? And so if the determinant is equal to 0, we would not get a solution at all. And the last one is a matrix has an inverse if it's a square matrix. Any questions so far about these facts? Cool. So here's a question for y'all. What is the product of, what is the inverse of a product of matrices? Somebody else. You got all the answers, but I love it. I love it. Anybody else? It doesn't hurt to give me the wrong guess, right? Come on, y'all. What if y'all got prizes for this? extra credit. All right, hit me. That's correct. So the inverse of a product of matrices is B inverse times A inverse. Now the key thing to note here is that the order of your matrices are inverted, right? So before when we spoke about the product of the determinant of matrices, we said that it was determinant of A times B, where we kept the same order. But when we talk about the inverse, that order reverses. Awesome. So now let's take a look at, so another additional example or another additional fact is the determinant of the inverse of a matrix is equal to 1 over that matrix's determinant, right? And so given this, let's take a look. So given this fact and the permutated LU factorization of A here, let's try to figure out what the determinant of A is, right? So the first thing that we would need to do is we would need to isolate A, right? And one way that we can do that is by multiplying by the inverse of P on the left. And with the definition of the inverse, we know that this is identity, right? And the multiplication of, identity times a matrix gives back that matrix itself, just by the definition. So you end up with this. So now we have isolated A, which is perfect. We can now proceed to take the determinant of A, which is simply this. And using the previous facts that we learned of the determinant of a product of matrices, we know that we can rewrite this as the determinant of P inverse times the determinant of L times the determinant of U. And we can further simplify this by using this fact right here, which gives us that the determinant of P inverse is 1 over the determinant of P. So this is the solution we get. Any questions so far? Cool. All right. Moving on to the transpose of a matrix. So the transpose of a matrix, essentially what it is, it's where you take the columns of your matrix and you essentially swap them and you make them the rows of your transpose matrix, and vice versa. So for instance, if you had a matrix A here, which I'll rewrite it, 1, 2, 3, 4, 5, 6. I wasn't very creative. Could anyone tell me what the transpose of this matrix would be? Yes.
1, 4, 2, 5, 3, 6.
Correct. Exactly. That's exactly it. So the transpose is really, you just take the columns and you make them your rows. And you keep doing that over and over again up until you're done. So some properties of the transpose of a matrix is that if you take the transpose twice, you end up with the original matrix. If A is a square, then the determinant of the transpose of your matrix is the same exact thing as the determinant of that matrix. You may ask yourself why, and it's actually not that hard to prove. So if you're curious about that, you can come to me after class or during office hours. And the last thing over here is this property, which is the product, the transpose of a product of matrices. And similar to the product of the matrices, the product of the inverse of matrices, we flip the order here again. Any questions so far? Cool. All right. Moving on to linear combinations. So a vector V in N is said to be a linear combination of vectors V1, V2, up until Vm, if there exists real numbers, alpha 1, alpha 2, up until alpha m, such that your vector V is equal to that. Does Does this make sense? No, that was just a bunch of like math mumbo jumbo thrown there, but we're gonna take a look at an example real quick. So let's go ahead and take a look at an example. So if I have a vector v here, which is a column vector comprised of the elements 11 and 7, the question here is this vector a linear combination of v1, v2, v3, right? So off the bat, there's multiple ways that you can do that. You can sort of throw darts at your target and try to guess what those coefficients could be. Or you could work this out mathematically in an algebraic fashion. So off the bat right now, just because of time, I'm going to say that we know what the coefficients are. In the next example, we will see exactly how we can get those coefficients. But for now, let's just say luck was on our side. And lo and behold, we guessed that alpha 1 is 2, alpha 2 is equal to 1, and alpha 3 is equal to 3. So the way that we can figure out if this is a linear combination, if V is a linear combination of V1, V2, and V3, is by simply solving this equation right here. So what does this give us? So you have 2 times the vector V1 plus your alpha 2, which is 1, times your vector V2 plus alpha 3 times your vector V1. And just doing the math here, we get that this is 6 plus 2 plus 3, 8 plus 2 minus 3, which, lo and behold, gives us 11 and 7, which is equal to V. So here we can say that V is a linear combination of V1, V2, and V3. Any questions about that? Okay, awesome. So moving on to the next example. We're going to do a similar thing here. So the first thing we're going to write is, what we're trying to figure out is, is V a linear combination of V1 and V2, right? And so we can go ahead and substitute in the V's with our actual vectors. Alpha 1, 1, 2, 3, plus alpha 2, 2, 1, 0. And so what this gives us 3 equations, right? The first equation being alpha 1 plus 2 alpha 2 is equal to 7, right? The second equation being 2 alpha 1 plus alpha 2 is equal to 5. And the last one being 3 alpha 1 is equal to 4. Ignore that plus sign. Let's see. Is equal to 4. How would y'all propose that we go ahead and solve for the alphas? So given this, what is alpha 1? What is it? Exactly. So alpha 1 is 4/3. So what now? I know that alpha 1 is 4/3. How do I progress? Exactly. So let's call this equation A, let's call this equation B, this equation C. So we're going to substitute alpha 1 back into equation B, right? And so that would give us 2 times 4/3 plus alpha 2 is equal to 5. Here we can solve for alpha 2 as 5 minus 8 over 3, which is 7 over 3. Cool. Are we done? No. Okay. Why are we not done? What's left?
You need to just check to make sure it works with the last equation.
Exactly. So we need to check with the last equation. So let's check with A. Right, and so with A, we would have 4 over 3 plus 2 times 7 over 3, which here would give us 4 plus 14 over 3, which is equal to 18 over 3, which is equal to 6, which is definitely not equal to 7, right? So what does this tell us? This tells us that V over here is not a linear combination of V1 and V2, right? Any questions so far? Does this make sense? Awesome. Perfect. We're going to move on to linear independence. So what does it mean when we say that vectors are linearly independent? So I think y'all learned about this and you wrote a function that would check whether vectors are linearly independent in lab. Is that correct? Yeah, okay, cool. So just another review here. So the vectors, we say that vectors v1, v2, and so on are linearly independent if and only if the only real numbers alpha 1, alpha 2, and so on, yielding a linear combination of vectors adds up to the 0 vector. What does that mean? That means that if I had vectors v1, v2 up until vm, the only real numbers, alpha 1, alpha 2, up until alpha m, that yield a 0 vector here are 0 themselves. So let's take a look at at an example. Does that definition make sense? Does that definition make sense on this side of the room? Yeah? Cool. Cool. Awesome. So the first question here that we're going to try to address is to determine if the following vectors are linearly independent. What's the first thing that I would need to do here? I want an answer from this side of the room, or at least an attempt. Given the definition here, if I want to figure out if V1 and V2 are linearly independent, what's the first step I should take? Any takers? I'll give you a hint. It's similar to what we were doing before in the previous page. Any takers on this side? Yes.
I just did the same thing, so it's equal to 0. I got vector 0, 0.
Exactly. So we would have alpha 1 v1 plus alpha 2 v2. And we would set this to 0 and see whether alpha 1 and alpha 2 are zeros or whether they're another real number. So moving on and substituting these with the vectors that we would have alpha 1 times v1 plus alpha 2 times v2 is equal to 0, 0. So this gives us two sets of equations, right? The first one being 4 alpha 1 plus 2 alpha 2 is equal to 0. The second one being alpha 1 plus 3 alpha 2 is equal to 0, right? And so using the second equation here, we can solve for alpha 1 as being equal to minus 3 alpha 2, right? We can then take this solution and plug it back into our first equation here, which would give us 4 times negative 3 alpha 2 plus 2 alpha 2 is equal to 0, which gives us that alpha 2 is equal to 0. And because of this equation here, we know that alpha 1 is equal to 0. So by solving the systems of equation, we now have that alpha 2 is equal to 0 and alpha 1 is equal to 0. What does that tell us in terms of linear independence? So in terms of linear independence, that tells us that these vectors are linearly independent. And that's because alpha 1 and alpha 2 are both zeros. Any questions about that? Cool. All right, I'm going to have y'all try to do number 2. Yeah, attempt number 2, I guess, in the next 5 minutes or so. And let me know if you have any questions about that. Oh, I should note, one thing to note is that number 2 is the same as the previous example 1 here, where we were checking for the linear combination. So what we're trying to get at here is what's the relationship between linear combination and linear independence. So. All right. Has everybody at least gotten to start the problem? See some people still writing. All right. Because of time, I'm going to go ahead and get started on the problem with y'all. So the very first thing that we should have written is that what we're trying to solve for, given the definition of linear independence, is we're trying to find, whoops, Tribby, what happened? Okay, that's okay. So we're trying to find the numbers alpha 1, alpha 2, alpha 3, and alpha 4 such that alpha 1, v1, plus alpha 2, v2, plus alpha 3, v3, plus alpha 4, v4 is equal to 0. That's what we're trying to find, right? One thing to note here, this problem, what we were doing before in the previous page is we were trying to find whether v was a linear combination of v1, v2, v3. In our new problem, v is now the vector v4, right? From the previous problem, we found that alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 was equal to v4 when alpha 1 was equal to, I forgot what it was, when alpha 1 is equal to 4, alpha 2 was equal to 2, and alpha 3 was equal to 3. Alpha 1 is equal to 1 here. Whoops. Right? Do we all recall this? So the problem that we're now trying to address is this over here. What is alpha 1, alpha 2, and alpha 3, as well as alpha 4, what do they need to be in order for us to get 0 when we do the linear combination of these vectors? And so off the bat, I'm going to say, let's try alpha 1 is equal to 4, alpha 2 is equal to 1, alpha 3 is equal to 3, and alpha 4 is equal to minus 1. If you try that, what do y'all get? Yes?
I was going to say, didn't we get that alpha 1 is equal to 2 alpha 2?
Yes, we did. Thank you so much. Thank you. I appreciate that. Yes. Yeah, yes, we did. What happens when you plug this back in to the equation over here? What do y'all get? So writing it more explicitly, you'd have alpha 1 times 3, 4, plus alpha 2, 2, 2, plus alpha 3, 1 minus 1, plus alpha 4. This would give you two equations. Alpha 3 plus 11 alpha 4 is equal to 0. So if you plug in these alphas into these two equations, what do you get? Is it indeed equal to 0? Yes, I see a nod, yes. It is equal to 0. Now, the question is, what does that tell us about linear independence? It is not linear independent. It is not linearly independent, or these vectors are not linearly independent, right? And so what we can conclude in general is that if you have a vector v4, and if that vector is the linear combination of your other vectors, all of those vectors, v1, v2, v3, and v4, when you put them together, are not linearly independent from each other. Does this make sense? So I'm going to say it one more time. If v4 is a linear combination of v1, v2, v3, then v1, v2, v3, and v4 are not linearly independent. This will come in handy. This might come in handy on your homework. Okay? And you can generalize this result, however many vectors that you have. Any questions about that thus far? Yes.
You also say that if a vector is a linear combination of other vectors, is it linearly dependent?
Yes. Yes, exactly. All right. So here, what we're going to do is that we're just going to set up this problem and then move on to the Julia portion of things. But let's say that we have a system of equation ax is equal to b. We know that we know a solution exists if b is a linear combination of the columns of A, and if the columns of A are linearly independent. So, given what we know about linear independence and linear dependence, how exactly would we go about solving this problem? And so what we would do is that in order to figure out whether the columns of A are linearly independent, we would need to solve, so okay, let me see. We can essentially take this and write this as a matrix as follows: -1, -2, -3, 3, 0, 3, 5, -2, 4, times A, B, C, and this is equal to 20, -8, and 10. All right. So this, call this V1, call this V2, call this V3, and this V4, right? So if we wanted to figure out if the columns of A are linearly independent, what would we do? We would follow suit. We would do the same thing as we did in the previous example, which is we would do alpha 1 plus V1 plus alpha 2 V2 plus alpha 3 V3 is equal to 0, right? And we would try to see whether or not we could find real numbers alpha 1 and alpha 2 and alpha 3 that were not 0 that could solve this equation for us. If alpha 1, alpha 2, alpha 3 are not 0, then we know for a fact that V1, V2, and V3 are dependent. If alpha 1, alpha 2, and alpha 3 are all zeros, then V1, V2, and V3 are independent, right? All right, for the second part, which is figuring out if B is a linear combination of the columns of A, we would do something similar to this, right? Where we would have alpha 1, V1, plus alpha 2, V2, plus alpha 3, V3. We would try to see if this is equal to V4. We would solve for, I guess I should do tilde here, right? We would try to solve for alpha 1 tilde, alpha 2 tilde, and alpha 3 tilde such that we get V4, or we could do alpha 1 tilde V1 plus alpha, let's call that bar, alpha 2, whatever, plus alpha bar 3 plus alpha bar 4, V4, and try to see if this is linearly independent, right? If you solve for this and you get that alpha bar 1 up until alpha bar 4 are all zeros, then we know that V1, V2, V3, V4 are all linearly independent, and that B is not, and that V4 is not a linear combination of the previous vectors. Cool. Any questions about that so far? Sorry, I know I scrolled too fast. All right. And I'll upload a much more cleaned up version of this that doesn't have all my scribbles on it. Cool. The very last thing that I wanted to talk about is a way that, or just a couple of facts that combine what we've learned about linear independence, the determinant, and the inverse. So given a matrix A, which is comprised of the vectors V1, V2, V3, up until Vm, the set of the vectors V1 are linearly independent if and only if, so they're linearly independent if and only if A is invertible, and that happens if and only if the determinant of A transpose times A is not equal to 0. So given this fact, try to think about how you would solve for problem 7 differently. You could solve for it using the determinant, or you could solve for it using linear independence. Yeah, any questions about that? Awesome, perfect. Trivia, you wanna come over?
I'll take the mic.
Oh.
So, I think, I don't know how comfortable people are with writing functions in Julia. Are we good with it? Do we understand the syntax, what return means, how to call a function, how to define a function? Now that throws us off, right? And we're pretty comfortable with it. Okay, so going over the basic syntax, you define a function, then the name of your function, that's what you're going to use when you're calling your function later. Then you can have some arguments, it can also be empty, and we're just writing a simple function where we return a square plus 1. And then you see the return statement, which returns the variable that function is giving out, which is basically if you want to assign a value that the function is returning, then it needs to return a value. If it doesn't return anything and you try to say a is equal to square plus 1 of 10, it's going to return an error, right? And then the end statement that tells us that the function block is over. So we write that, and this is a sample function call. So for variable 10, I said a new is square plus 1 of 10. And because Julia is flexible with the argument types, like you don't have to specify that you're going to send in an int or a float. So I can send in an integer, or I can send in a float number, and it will just determine the type for itself. So it's a lot easier. So we know how to write functions, and we know how to calculate matrix inverse of the 2 cross 2 matrix. I think this is also in your homework assignment. So we have a formula, and are we comfortable writing it down in a function? Should I just quickly do it? What do you say? Yeah? No? Okay. Are we doing it? Is anyone else doing it?
Can we access the recitation?
It's in the files. I didn't make it an assignment because it's usually like a shorter notebook. It doesn't make sense. So we have a matrix A. Would it be easier to do? So let's extract out the different, just so it's easy. Does this make sense why I'm doing this? So I just want to use that formula. Yeah? There's a better way to write this probably. Then I'm not going to use the determinant function. I'm just going to say determinant of A is A times D minus B times C. And I'm going to call the matrix a joint of A. And I'm going to fill that up with D minus B minus C A. Does that make sense? Right? So now what do I return? What would be the return statement? Yeah.
Would you return like 1 over the determinant of A times adjoint A?
Okay, yeah, that works. So 1 over determinant of A in brackets here times B adjoint A. Does that work? Right? Functions are easy, useful, and then every time you have to call a 2 cross 2, you have to find an inverse of 2 cross 2, and you don't want to use the inverse function, which you could, you can use this. The idea is that we're comfortable with the whole function syntax, right? So we've been beating this drum in lectures a lot, where we're saying that don't use the inverse function, it's bad, we should use the LU. And we've been claiming that it's usually faster. So I just coded up like a random 5,000 times 5,000 matrix A. And if you run it, it takes a while. You use the Julia function inverse, and that should print out a time in a bit, 7 seconds about. And then I use the LU factorization, right? We've seen the syntax before. And then we calculate the inverse. We remember that inverse, if you have the LU, inverse of A is inverse of U times inverse of L, right? We just did that. So let's see how much time that takes. Now, you'll notice that the syntax is a little weird, like I have to, oh, it was doing a lot better before, I don't know what happened. I swear it was half the time. But what might confuse you is that I'm using this upward triangular, because the way that we've been explaining it is calculating inverses of triangular matrices is a lot easier. And unless I specify that U is an upper triangular matrix, Julia is not going to use its special triangular matrix inverse formula, which is a lot faster, which is why we're using LU in the first place, right? Similarly, we can write down our own determinant of LU function, but like we talked about with Eva, the determinant of A times B, you keep the order doesn't matter at this point because these are scalars, right? And then the determinant of A times determinant of B. And using that logic, the determinant of A is then the determinant of L times the determinant of U. It's a lot easier to compute the determinant of triangular matrices because we know that the determinant is what? For triangular matrices, product of the diagonals, right? And which is also what Julia uses if you do specify that these are actually upper and lower triangular matrices. So I'm going to skip that one, and we're going to see the time comparison in just calculating the determinant. 1.6 seconds, and then this one is 0.02 seconds. So when you have like big matrices, calculating determinants and calculating inverses, you want to stick with, you want to use LU factorization. That's why we're telling you it's faster, you can do it in real time, it's the best thing in the world, right? Convinced? Sold it? Yes? All right. And last thing that we're going to go into is just, are we comfortable with the whole LU with the permutations? Yeah, we did it last recitation also, and we've done it in our homework. It's also in homework 4. Yeah? Okay. I think if you're having trouble with the permutation matrices, I was going to go over an example. You still want that? No? Yes? It'll be fun. We'll do it anyway. So it's kind of like an intuition where your permutation matrix is basically, I'm going to give you a rectangle, right? And the points are defined in here. And once I deserialize those points, the x and the y coordinate, I build a B matrix called which has all these points, x1, y1, x2, y2, x3, y3, and so on, all the coordinates of the rectangle. And then I'm going to ask you to find the permutation matrix that will give me this hourglass figure. Do you have an idea how that would be? Simple permutations. Does it make sense why this would be a permutation? So I have a square, right, with its x and y coordinates. How am I making that square? X coordinate, y coordinate, x coordinate, y coordinate, yeah.
Could you just flip the bottom 2 points, so what order they appear?
Yeah, so basically, if I say first point and then make this the second point instead of this one, and then from this one, I straight away go to that, like swap those two, it would make that figure, right? Right? So what would be the permutation for it? So let's talk just in terms of coordinates. I give you 4 coordinates, 5 to complete the whole thing. Which coordinates are we flipping? So if I have to write something like small p, which is not the right permutation matrix, we agreed that first one should be in place, right? Because the first one is this left edge right here. Then the second one, skip this one, I want to go to the third one, right? So the second one should be the third, right? And from here, I go to the fourth. And then from the fourth, I go to the second. Does that make sense? And then from the second, I go to the first, which is essentially the fifth. Fair? No? That's our order of points. What would be the order of the permutation? What would be the permutation matrix? No? Okay, what I'm also going to do is, because it's x and y coordinate, I'm going to make this 3, 3, 4, 4, 2, 2, 5, 5. Yes?
So your permutation matrix is just, so for the first row, it would be 1, 0, 0, 0, 0, because we're doing an identity matrix, right?
Yeah.
But we're shifting around the rows.
Yeah.
Since the first coordinate is in the same place, we're going to keep like that as 1, 0, 0, 0, 0.
Yes.
And then since the third point is now in the second place.
So flip the second and the third.
Sorry.
Flip the second and the third.
Yeah, you're flipping the second and the third. And then the fourth one, you're flipping the fourth and the third. But yeah, you're flipping the fourth and the third, and since 2 is now in the third, it'll be in the fourth as well. And then 5 is the same.
Yep. So, how do you form identity matrices in Julia? It's not I. No idea. Actually, I do have an idea. It's too big to write down. Which one? No, I think this one is fixed. Oh, it's not. Is it the capital I just? Do I write it down? Oh. Ah. Yep. It's my fault. We want to switch first. Here's a write this down. Second, third,